Hey everyone, welcome to my first video on my new YouTube channel. This channel is going to cover topics related to statistics, meta-analysis, psychometrics, data visualization, and so forth. This first video, we're going to focus on equal effects meta-analysis, what it means, and how we can apply it in R. So, starting with definitions, an equal effects model assumes that all observed effect sizes in a meta-analysis are estimating the same underlying true effect. So consequently, all the variation in observed effect sizes across studies is attributable to sampling error. So let's take an example. Say we have 12 studies investigating the difference in vocabulary knowledge between people with and without a college education. So each study uses the same 10-item vocabulary test, where the total number of words correctly answered out of 10 is our outcome variable of interest. So our effect size of interest here is the mean difference in the number of correct responses between people with a college education and those without. And we'll denote the people with a college education as 1 and the people without a college education with 0. We'll also denote it with red and blue, respectively. So the true mean of group 1 can be denoted by mu sub 1, and the true mean of group 0 is mu sub 0. The difference between those true means is our true effect size of interest, which is the true mean difference. And we'll denote that with the capital delta. So for an observed effect size, each study calculates the difference between sample means. So M1 and M0 will be the sample estimate of those true means. And the difference between those is our sample estimate of our mean difference. And we'll always denote Greek letters as the true value and then the English letters as the sample or study estimate value, the observed value. So if we look at each of the studies, we can look at the distributions
of scores
within the college-educated group and within the group that is not college-educated. The non-college educated group is the blue histogram, and then the red histogram is the college-educated group. And we'll see that on average, pretty much across these studies, we kind of see a trend towards college-educated students, as we would probably expect. So the mean differences for each study vary a lot. So from study to study, there's lots of variability in our sample effect size estimate. That brings us to our model. So we know that, well, we're assuming that with the equal effects model, there's one true effect size that all of these studies are estimating. So why is there variation in the observed effect size? So in this model, we have our observed effect size for study I as DI, and then we have our true effect size, delta, and we have our sampling error term, which is essentially defined as the difference between the true effect size for a given study and the observed effect size for a given study. And again, true effect size for a given study is the same for each study according to this model. So what we are going to assume here, we're going to assume that the sampling errors are independently and identically distributed as a normal distribution with a mean of 0 and a variance equal to our sampling variance. So our sampling variance is going to be our standard error of the effect size squared. Okay. This would indicate that each or the distribution of study or observed effect sizes is also independently and identically distributed as a normal distribution with a mean of the true effect size and a variance VI. So you can have a different sampling variance for each study. So what do we want to estimate in our equal effects meta-analysis? So generally, we want to estimate this true effect size, right? So what we can do is we can take an average of the observed effect sizes and hopefully that will give us a more precise estimate of the true effect size of interest. So what we can do is we can take a weighted average, and this formula here just takes a weighted average using weights W of each observed effect size for each study. Now the weights here is going to be the inverse of the sampling variance. And the reason that is because with less sampling variance, the more precise the study is. Essentially, we want the most precise studies to be weighed the most. Here, we can compute the standard error squared, or the sampling variance of the estimated true effect size, by taking essentially the harmonic mean of the sampling variances, or the inverse of the sum of the weights in this case. So for the case of mean differences, we can calculate the sampling variance by essentially taking the variance of the data, the variance of the scores, the vocab scores of group 1 from study I and group 2 of study I, and divide them each by their corresponding within group sample size. So the sample size of the college students and the sample size of the non-college students. So let's take an example from study 1 in our data set. So in study 1, they report the college educated sample and the sample with some college or less. We have 19 individuals in the college educated sample and 30 in the some college sample or less. We have means of 7.79 and a standard deviation of 1.51 and a mean of 4.7 and a standard deviation of 1.90. So clearly the college educated group has a higher mean than the some college or less group. So we can calculate the observed effect size for study 1 by taking the mean difference. So 7.79 minus 4.70, and we get an average difference of 3.09 words. Okay. And then we can also calculate the sampling variance by taking the standard deviations from that table and the sample sizes from that table, and we get our sampling variance for this study. So we can do this in R as well to make this process much easier. We can first load in the data set from my GitHub repository with this code here. And then we can just take a look at the data set. So here we have the study column, study ID. We have the sample sizes for each group 0 and group 1. We have the means of each group and the standard deviations of each group. So we can use the metaphor package in R. And within that package, there's an escalc function which calculates our effect sizes for us. So using the escalc function, we put in our data set, which is stored as df. We can set the measure to be MD for mean difference. We can then input the statistics from our data set, so the means, the standard deviations, and the sample sizes for each study. And then we can have the output just label them properly. So we want to use DI for our mean difference and then VI for our sampling variance. So let me just move my face out of the way. We see that in the data set, now we have appended 2 more columns, DI for our mean difference and VI for our sampling variance. Okay. All right, now we can actually estimate the parameters, and the metaphor package allows you to run meta-analyses. So we're going to run a equal effects meta-analysis using the RMA function. We'll input our new data set with the appended columns for our mean difference and our sampling variance. We'll use the YI argument, which is for the effect size of interest, and then VI for the sampling variance. Then importantly, we have to set the method to be equal effects, or EE here. Now the output, so the coefficients from this study show us our average mean difference here, which is essentially going to be our estimate of our true effect size. It shows the standard error of that estimate, also the z-value and the p-value, and as we can see, it's 5.7 e to the negative 35, so it's going to be highly significant. Um, and we have our confidence intervals, our upper and lower bounds of that value. I'll have a whole video on confidence intervals at some point. So the next thing we might want to do is we might want to test the assumptions of our model. So in the equal effects model, the major assumption here is that all the variance of observed effect sizes across studies is attributable to sampling errors. So how can we test this? So we're explicitly assuming that the variance in the observed effect size equals the variance in sampling errors, right? So what we can do is we can first estimate the variance in observed effect sizes by taking the weighted average of the squared deviations of the observed effect sizes from the estimated true effect size. Then we can take an estimate of the variance of sampling errors by essentially just taking a weighted average of the sampling variances for each study. And with the equal effects model, these two estimates should be approximately equal. So we can do this in R by essentially using the weighted.mean function, which is just base R, and then we can feed in the variance, and this is for the expected variance of mean differences, which is our sampling error variance. So for the sampling error variance, we can put in the sampling variance for each study, and then put in our weights, which again is the 1 divided by the variances. So we get a value of 0.312 in our example, and then we want to calculate the observed variance of mean differences, and similarly, we can use the weighted mean function. We can input the squared deviations, essentially taking the observed effect sizes and subtracting them by our model estimate, which is our true effect size estimate, true mean difference estimate, and then squaring that. So the average, the weighted average using the same weights, would give us our estimate of the observed variance in mean differences. Here's 0.351. So it's a little bit different and it's a little bit larger than what we would have expected from sampling errors alone. We can then test that with a hypothesis test. This test is called a Q-test. It's essentially a hypothesis test for heterogeneity. And what I mean by heterogeneity is that I mean that there's excess variance in our observed mean differences that's above and beyond what we would have expected from sampling errors alone. So if this p-value was less than the conventional 0.05 threshold, we could claim that there's significant heterogeneity in our data set, and then we might think that, well, maybe this model, this equal effects model, is not a good fit. So now if it's not significant, that doesn't necessarily mean there's no heterogeneity, although I do know that this data set doesn't have heterogeneity because I constructed it in that way. But it is important to do this Q-test just to test your assumptions about the equal effects model. So what I did to create this meta-analytic data set was I pretty much just took random samples from 12 random samples from the general social survey, which was pretty much a way to make sure that there was no heterogeneity. The true mean difference turned out to be 1.83. That's across all 30,000 or so individuals in the general social survey. So our estimated mean effect, mean difference was, if you recall, was around 1.9. So it did a pretty good job of estimating the true effect. Okay. So if you guys liked this video, go ahead, maybe drop me a like, maybe a subscribe, and I will get to more videos very soon.